organic chemical probe approach, I thought it was only appropriate to balance the other side of the coin and have a talk on the characterization of catalyst surfaces using positron spectroscopy. This talk will be presented by Dr. Chris Huang, Department of Physics, University of Louisville. Chris has received his PhD in physics from the University of Virginia. He previously has an MS degree in nuclear engineering from the University of Michigan, and also a bachelor's in physics from the University of Michigan. He's been with the University of Louisville since the mid-1960s. His current interests are studying positron annihilation techniques to apply them to various materials. His talk this morning will be on positron spectroscopy, a novel technique for the characterization of catalyst surfaces. Dr. Ewing.
Thank you. It's my great pleasure and honor to be here today with such a distinguished group. And if I ever give you a vague impression that I'm good in chemistry or in particular in catalysis, then you're totally misled. And ever since my college years, the chemistry is always the most feared subject for me. And even today, I'm still in the process of overcoming it. But ever since we do the Positron annihilation technique, and particular recent years, that I'm particularly excited by its applications in the study of catalysts. And ever since the discovery of positron in, say, early 30s, it was almost immediately realized that the gamma rays from the annihilation from the positron and the electron pair carries valuable information about the electronic property of the material they annihilate. But only in the 60s, I would say, that great advances were made because the advances in the instrumentation and analysis technique. So it has been applied to great variety of materials. You name the metallic material, alloys, semiconductors, everything. And in the recent years, that our group is particularly excited by its application in the porous material, particularly the catalytic material. And that's why I say I'm still trying to make up the chemistry knowledge here. So what I want to do today is to make an introduction of this positron technique and its basic principles, techniques, and show you a number of basic examples, and then show you some most recent results in its application to the catalytic material. So my presentation will be basically like this. First part we have it's the basic principle and techniques involved, and I'll show you the example that being used for the determining Fermi energy and the defects and a number of other things, and then the late recent application to zero lines. The basic principles is really rather simple. What you do is you have a positron source, usually from the radioactive material, and most time we use a so-called sodium-22, and then it goes into the solid material, and quickly you lose energy, so it becomes thermolite positrons, and the process usually takes only 10 to minus 13 seconds. So essentially, by the time it annihilates, all the positrons consider thermolites. And when thermolite the positron means electrons, it can annihilate free electrons. And this, of course, then goes into annihilation. And the lifetime, this is our lifetime, is about 10 to minus 10 seconds. Now, also it can form a bond system. This bond system, particularly interesting, is forming the Positronium. Right? It's a bond system of positron and the electron formation. And with this positronium formation, then it always ends up annihilation, of course, but it can form also positronium or parapositronium depending on state and spin arrangement. And for the also positronium, you end up with a 3 gamma annihilation, and the lifetime is relatively long. We consider long 10 to the minus second. And the parapositronium formation, it ends up with a 2 gamma annihilation, and the lifetime is much shorter. So during the process, usually this also positronium can be, let's see, oxidation. I mean, this is a conversion goes into parapositronium. The more interesting is this, that these 2 gamma rays, of course, will be basically emitting in the opposite direction. This opposite direction, but however, it will have an angular distribution there because of conservation energy momentum with the electrons. So the gamma ray will carry, we have certain angular distribution that will be proportional to the electron momentum distribution. The gamma spectrum, whether it's usually in terms of this momentum of the electron or energy of the electron, and usually you have two very shape. One is a broad Gaussian sort of like distribution, and then on top of that, for positronium formation, it has a distinctly different distribution, and that's the important part for our application. I'll show you later on. This slides will show you this basic technique involved there. You have 3 basic technique involved there. One is a lifetime, which will basically measure how long the positron stays in the material before its annihilation. Obviously, the more available electrons, in other words, the electron density is higher, then the lifetime will be shorter. If the density is lower, then the lifetime will be longer. So the information you got is this lifetime, say delta T. Delta T is simply the signal of the burst of the gamma ray for the sodium-22, because the positron and the gamma ray of 1.27 MeV, which emits about the same time, because the intermediate state is only about 10 to the minus 13 seconds, so this is considered simultaneously. So in other words, you detect 1.27 gamma, which indicates the burst of the electron. But when the positron goes into material, solid material, annihilate with the electron, then it tests by mc squared. The characteristic gamma ray is 0.211 MeV gamma ray. So this is very easy to distinguish, to separate. So the time lag between these two signals is called the lifetime, and the lifetime information is related to the electron density, basic electron density. Now the other way is to the two-photon angular correlation measurement. And let's look at this purple color of the arrangement first. This is called a one-dimensional angular correlation annihilation radiation. So we call this simply called 1D ACOR. Now 1D ACOR, basically you have a one detector, gamma detector is fixed, and the other detector is moving in the angular space. And the angular distribution is the delta theta angular distribution by the conservation momentum. And because the positron thermal light is practically zero momentum, so all the momentum carried by electron. So this angular distribution is proportional to this P momentum of the electron in that component, in that particular component. Now, obviously, if the material is isotropic, amorphous type of material, then it doesn't matter if this momentum components, the X, Y, they are the same. On the other hand, if you have a single crystal type, you have an anisotropic distribution, then you will see that all the different components are different there. Now, this process is a little bit time-consuming because you detect only the gamma distribution in this, say, called the Z direction. So the gamma counting rate is usually very low. Now the more advanced one is called the two-dimensional ACOR measurement, and that is simply you put a matrix of detectors on both sides, so that at the one shot you really measure the two momentum distribution of the electron in the material. And so basic spectrum you will see later, but basically it's something like this. If you call this the X, Y, and the electrons have a distribution either in the X direction or the Y direction, so you have a three-dimensional spectrum, something like this. The other technique is called the Doppler bottoming. Doppler bottoming is a very simple instrumentation. You have a positron goes into the material, you detect only 0.511 MeV gamma ray, and you have a high resolution detector. And because of Doppler effect, so you are measuring the energy distribution Doppler effect, in other words, in this X direction. So you get the distribution basically something like this. This is the broadening due to the electron motion. And this broadening, of course, related to the electron momentum. So this is a basic experimental technique. Now today I will particularly emphasize on this 2D echo measurement, because this has a greater resolution and also has a time efficiency in measurement and so on. This slide simply gives you some mathematical expression and simply tells you that this angular distribution, whether 1D or 2D aircraft or the Doppler measurement, it simply is when you have a 1D aircraft measurement, you have this momentum density, a 2 gamma momentum density there. You measure only one dimension, so you integrate out the two dimension. Obviously, the resolution suffers. But for the 2D aircraft, then you integrate only one direction, that is the X direction you're measuring. So you add less integration there, so you have a better resolution. And the D bar, this is Doppler effect of Doppler broadened annihilation radiation. And this is similar to the 1D measurement, except that you have it in a different direction there. The relative merits is simply this, because Doppler effect has an advantage of simple instrumentation, but the resolution is suffered as compared to the 2D aircraft. Now let me show you some examples in the past. This one, I think this is a copper. Anyway, some metallic material. And you can see clearly that this is 1D aircraft, so this is in the angular coincidence of the angle measurement. And this is corresponds to momentum distribution. And you can see the central part of this is conduction electrons, free electron density, free electron momentum distribution. This should be parabolic, and this is the central part. And this is, of course, a positron also annihilated with the electrons in the core electron, or the rest we call the core electron, which is more tighter bound. So have a larger momentum distribution. So you can see this distribution here. And clearly you have the breaker here. This is the Fermi momentum. And this is considered in a number of ways is a superior way to determine the Fermi energy for the conductors. And this is just a simple example, but there have been lots of these measurements, and you can determine very accurately the Fermi level. Now, also I want at this moment to show you the so-called user line shape parameter. In other words, that if you have a conduction electron has a change, say the free electron density changes, then this parabola will be, the area will be smaller. So this change of this angular distribution is monitored by this line shape parameter, which measures the ratio of the area is the central area, they call this A1 over the A0, the total area. So in other words, if you have a conduction electron changes, then this parameter will tell you corresponding changes. Now this is, of course, is an old story here. Then during the mid-60s, it was often discovered that when you have a defects in the material. This becomes a big business. What happened is initially that you have a piece of copper, say you measure the lifetime of distribution, and then you simply hammer it, pound it on it. You measure it, you found the spectral lifetime of the angular distribution changes. Then you anneal this copper, it goes back again. So that is a very exciting moment because you realize that the positron can be used to detect the defects in the material. So basically you have, say for instance, in this particular example, this I believe is copper, you heat it, and initially this line-shape parameter here, doesn't matter line-shape parameter lifetime here, and then you have initially have a volume expansion. This is due to volume expansion. Then you all of a sudden see this, we call the S-shaped curve, this sudden increase there. And this is due to the creation of thermally created defects, because once you have a monovacancy, this is corresponds to monovacancy. When you have monovacancy, the positron wave function tends to fall into the hole, so the concentrate in the hole there. So this is, if you take a radius plot of this area, then you will see a beautiful straight line, and the slope of the line, of course, tells you the entropy of the monovacancy. And this has been done lots of work and considered this is probably the most accurate measurement for vacancy thermal entropy determination. Probably is the most accurate one, because the information everything directly from the defect size. Now, the more recent and the important application is this is a year ago, 2 years ago maybe. This is application to superconductors. Now, I don't know how familiar with the superconductors. I'm talking about high TC superconductors. And of course, the theory is still today, there is no solid uniform theory there. But one of the theory is concerns with the question whether there is Fermi surface in the high TC material. And this is very important for the experimentalists to determine that. And probably the positron annihilation, the only experiment can provide a solid answer to that question. And this is the result of the measurement. This is from 2D angular correlation. And this is from single crystal of this high TC superconductor. And what happened is here, this is simply on the C-axis, and this is the AB plane. You sort of cut across there. This is momentum distribution. And this is well accepted because of the dark, this dark shadow there. You can see that this have a sharp cutoff. There is a sharp cutoff there. Yeah, sharp. You can see this area here, very sharp cutoff. So this is practically sort of proves that this superconductor it does the surface does exist. And that really modified number of theory, because it's all accepted. So this is a very important application to this. Now, like I said, what I want to do is specifically for the catalytic material. So I used 2D aircraft measurement, and also with Doppler measurement, so on. Now let me show you first of all what the physical setup for the 2D angular correlation measurement. This is the 2D laboratory, and these are matrix gamma detectors. You see the gamma detector there. This is sample chamber. So what we did is the particular example I'm going to show to you is ESM5, so that catalyst. And we put in this chamber there. It has a vacuum system and it has a positron source inside there. Now you have a matrix detector on this end. It's about 5 meters away, and also on this end. So this measures to the correlation measurement. And this is a close-up of the matrix gamma detectors. and they involve quite a bit computer software to correlate the data. Now, usually you always use this quartz as a test sort of sample for the system, and this is typical quartz data. And this is the X and Y to momentum. This is the momentum axis there, and this is the central peak here is the Positronium peak. Positronium peak have a much narrower peak. So there's no ambiguity that where is the Positronium here. Now those small peaks is you consider this is different Freelon zones. Yeah.
Time.
Oh, I see. Okay, let me hurry then. Now, when you apply to the porous material, let's see this slide. Consider this the bulk solid materials, and you have internal channels, internal space there. So you have internal surfaces there. So you look at when the positron enters the material, it may annihilate in the solid material, but no positronium. You cannot form positronium in a crystalline structure there. So you annihilate, this contribute to the broad distribution there. But you can also have the positron migrate to the surface and annihilate with the electron in the near surface, they form positronium. This positronium will diffuse through the space until annihilate. But keep in mind that this will have a completely different distribution. Furthermore, that if this have oxidation sites there, the positronium can be oxidized. That means what? That means it reduces the population of positronium. That means it reduces the central peak intensity. So that means we'll change the so-called line shape parameter. That's the basic principle application here. So now, first of all, we show number of slides and number of these work. This is in a 5 physics letter. They are alumina, and simply we vary the surface area first, and you have a line shape parameter there. And you can see indeed that if the surface area increases, you increase the probability of positronium formation. So that is increase there. And then you have different materials, different zeolite A. You have a 3 or 4, 5 diameter. So this is you plot this line shape parameter with a d squared. So this is whatever the shape, it will be something with the area, and also you have the nice correspondence. And in this one, you pick a different material. Different material with different surface area, and you can see also the line shape parameter increases. This is simply verify that the positronium forms on surface. And then we take this ZM5. This is TGA data for the ammonium ZM5, and first of all, this is the TGA data, and in this temperature reaching about 250 to 500 there, and you can see that this is have a thermal decomposition there. So that means that means it goes into ammonia as it goes away. So this is as the temperature increase this way, you increase the protonic acidity there. Protonic will reduce the positronium population by soda oxidation. Right, so you see this 2D ACAR measurement. This is 2D ACAR measurement of ZM5. This is the two-dimensional spectrum. This is cut away of this spectrum, and you see clearly this positronium peak there. So now if you compare these two measurements, TGA and this TGA and this 2D ACAR measurement, you recall that a moment ago, this is TGA in this temperature region, and you look at this data also in the same temperature region, and it drastically decreases because you have increased acidity that reduces the positronium intensity, so that reduces the line shape parameter. And this we use two methods even. One is open circuit with 2D ACAR, another one with the dark blue broadening measurement is a solid circle, and they all agrees very well. Now, eventually, of course, you want to relate it to not just acidity, you want to specific acidity. That is acidity per unit area. So we measured those samples by independent method of the area and find this specific acidity. And this is also the MC5. And although there's only 4 data points there, but it shows very well this light shape parameter here, and this is a relative specific acidity there. And this is indeed what we expected, because this is the 1 over area, so when the area increases, so 1 over area should decrease, and also when acidity increase, it will also decrease. So the light shape parameter can be correspond very well to the specific acidity. Now, our current work, of course, goes into a lot more than this. We have all other catalytic material in process. But the initial result here is rather exciting to me, at least. Okay, I hope it will take too much of your time. If you have any question,
I think we have time for a quick question.
Yeah.
What is the mechanism of acidity-induced positronium disappearance?
What positronium? You have positron and electron, and you have a proton. Proton take the electron away, so that breaks the positronium. So you reduce the intensity. You reduce the intensity.
All right, one other question.
You said it's only good for detecting bronze acids, right?
Yeah, I would say that so far in the case, I mean, simply, I think that you see a stronger those bronze acid sites are more effective in the oxidation.
Well, your alumina data shows that it is responding to positrons. And alumina doesn't really have very much bronze acidity.
No, it does not. I mean, all I say is that is nothing with the acidity there. This is simply surface area. When you increase the surface area, you have a more probable probability forming the positron. That's what I think. This is simply used to verify the conviction that this is forms on the surface.
When you showed the ZSM5, the slope was downward. Am I to interpret that as being that the acidity decreases there?
No, this is acidity increase because this is the acidic, specific acidity per unit area, So both of these factors, acidity will reduce it, and the 1 over area also reduces. So this is perfectly as we expected.
But is this the same ammonia to proton ratio?
The same samples, and all this is the same sample. We simply used this measurement divided by the area measurement. Yeah.